Good morning, aspirant. So what you are going to learn in this video? In last class, we have discussed three types of conductance. And now, as we have discussed that, we will be studying electrolytic conductance in details. So this and onward topics will be electrolytic conductance. And in electrolytic conductance, in this video, conductance, in this video, you will be learning Ohm's law, OHM, Ohm's law. There is another Ohm's law for a metallic conductance, V equal to IR. We all know that, right? Next, from Ohm's law, after discussing Ohm's law, we will be discussing some key points about Ohm's law. That will be very important points which you should know about Ohm's law. Second one, we will be discussing type of conductance, type of electrolytic conductance, electrolytic conductance. So there are three types of electrolytic conductance, and about all of them we will be discussing. Three types are specific conductance. I am writing just short form: specific conductance, molar conductance, and equivalent conductance. Equivalent conductance. Specific conductance has another name, that is conductivity. Conductivity. So three type of conductances are there. Okay. Now let's start with Ohm's law. Ohm's law says resistance in electrolytic conductance will be proportional to L upon A. What is L and what is A? Suppose in any electrolytic conductance medium, there are two different electrodes of same area. The area of the electrode is basically A, and the length between these two electrodes is L. This is L. Okay. Now this L by A, this whole term L by A equal to, you can write phi, that is cell constant. Cell constant. This is another term. L upon A is called cell constant. Okay. So this is resistance, length, area. If we want to replace this proportional to with equal to, then we can write R equal to one constant. The constant is basically rho into L upon A. This rho is called specific resistance. Specific resistance, because from resistance equation this constant is coming. That's why it is called specific resistance or resistivity. Resistivity. Okay. Now if we are going to discuss, we are more concerned about conductance. We know more the resistance, less will be conductance. Think logically. Wherever there will be more resistance, then conductance will be lower, right? So resistance is basically 1 by conductance. Okay. So if we inverse this whole equation, that is 1 by R equal to 1 by rho into A by L. Now 1 by R can be called as conductance. Okay. C, suppose, because conductance is nothing but inverse of resistance. Equal to 1 by rho, it is again a constant. So let's give it a name, another figure called kappa into A by L. Kappa is called, as from resistance equation the constant is coming, that's why it is called specific resistance or resistivity. From conductance equation it is coming, so it is called specific conductance or conductivity. It is basically this conductivity, kappa. Okay. Now your work is to find out the unit of rho and kappa. I think you can do that, because resistance unit, you know, ohm. L means length, that means in CGS it will be centimeter. or in SI it will be meter, and area is semi square or meter square. Okay, so I think you can calculate you can derive the unit of rho. For kappa it will be uh, it will be 1 by r, that is conductance. For kappa, if we want to calculate the derive the unit of kappa, that will be C means conductance. It is basically 1 by ohm. So that will be 1 by ohm equal to kappa into area upon length. Overall unit will be centimeter, isn't it? Centimeter square upon centimeter. So centimeter only. So 1 by ohm, it is basically called Siemens. Okay, Siemens. Or it will be called like this. It will be called mho, mho. It is basically inverse of ohm. So 1 by ohm is sign is like this. Also it is called Siemens. Okay, or S. So unit will be kappa unit will be mho semi inverse, right? Semi will be semi inverse or Siemens meter inverse. Okay, I hope you have understood this. Now there are some key points. So let's discuss these key points about Ohm's law here. Now, if we want to discuss the key points, first key point is R proportional to L upon A. Whatever properties are depending upon length, okay, overall it is proportional to 1 by length, right? Basically it is centimeter and it is centimeter square. So overall it is inversely proportional to unit of length. So it is basically extensive property. Extensive property. Okay. And lambda, as it depends on, it is basically nothing but 1 by r, it is equal to 1 by r. So as lambda is extensive, sorry, as r is extensive, then lambda will also be extensive. Extensive property. Now what does this indicate? Suppose I have one solution A, it has conductivity lambda 1. Okay. Now what is lambda actually? In this section, C is sometimes written as lambda. Okay, C or lambda. Suppose it is lambda 1 in this solution. Suppose in this solution it is lambda 2. Now if we mix those solution, then extensive property means additive property. Then lambda total will be just addition, lambda 1 plus lambda 2. Whenever any property is extensive property, then we can add that. Okay, extensive means additive. But the thing is, kappa, this one, specific conductivity, that is kappa. Kappa is intensive. So intensive properties you can't add upon, right? You can't add intensive properties. Suppose in this solution it is kappa 1 specific conductance, it is kappa 2, then kappa total is not equal to kappa 1 plus kappa 2. Okay, I think you got my point. Okay, so first point of key points is R or lambda both are extensive properties, so we can add them, but kappa is intensive property. Okay, now third key point. Okay, first key point is this, second key point is kappa, third key point is V equal to IR. We all know it is basically simple Ohm's law, right? And we know R equal to, we have learned R equal to rho into L upon A. This is basically Ohm's law for this electrolytic system. Now there is something called current density. I'm going to next slide. Okay, it is there is something. So third point, there is something called current density. Current density. Current density is denoted by J. Current density is current flow per unit area. Okay. So J is basically current flow means I upon area. I equal to, from Ohm's law we know, V equal to IR, isn't it? So I can be replaced by V by R. So V by RA, right? Now we know R equal to rho into L upon A. From Ohm's law, R equal to rho into L by A, we know. So R into A means rho L. So V by rho L. Okay. So RA I am replacing with rho L. Okay. From here we can write RA equal to rho L. So V by rho L. Now we can write V by L into 1 by rho. Now V by L is called actually E. It is called electric field. Electric field. Okay. Electric field. Why I am telling you these things? Because in some competitive exams, they ask from some physics oriented things sometimes. So that's why I think you should know this. This is basically electric field. Okay. Voltage per unit length, that is electric field, into 1 by rho means basically kappa, isn't it? So the formula is J equal to EK, electric field into kappa. So this formula we have derived. So these are three major key points here. Okay. So I am closing this lecture here, and in the next video we will be discussing this three type of conductance and their interconversion and so on and so forth. So till now, if you have reached till end of this video, congratulations. You have a good patience level. Okay, thank you. Meet you in next class.